Okay, good day to all of you. Now, let us try to solve this circuit using nodal analysis. This is from the book of William HAYT. No, if you want to search, that is a book of William HAYT. I forgot what the edition is, but this is problem number 8. And also, we will check if our answers are correct. No? So we will apply KVL and KCL in the end for us to verify if our answers are correct. Okay, so let us try to solve this one. So we have here in the circuit of figure 4.34, determine the current labeled I with the assistance of nodal analysis techniques. Okay, so we're dealing now with nodal analysis. So how can we deal with this? So let me try to redraw the circuit, or let me just copy this one first. Okay, Control C, Control V. Okay, so that is one. So steps in using or in techniques in solving nodal analysis is you need to assign some current directions for each passive elements. What are the passive elements? Ito yan, yung mga resistors. It is the resistors, no? So assuming that this is B1, B2, and definitely last node will be our ground. Let me just have a color blue, no? And let me just change its size. So this will be the ground, reference ground. And this is 5 amperes, 4 amperes, B1, V2, 5 ohms, 1 ohm, 2 ohms. Assuming that the direction of current, let's just say color red, current direction going down. That would be, let's say, I1. And the other one is I2. Okay? So we have I1 and I2. So we assign the values or directions rather on the resistors. Then apply Kirchhoff's current law. So KCL at node B sub 1. Okay? So the current at node B sub 1 is or KCL states that the sum of all the currents entering a node must be equal to the sum of all the currents leaving. So 5 ampere is entering through V1. So definitely that is 5 amperes. And then I1 is leaving. So definitely equals I1. And also the current I is leaving plus I. So rearranging the equations, or let me just fix this one for a good looking. So I1 plus I is definitely equal to 5. But we can say that I sub 1 is what? I sub 1 is just only the potential difference of the element over the resistance. So let's just say this is I1. Definitely the potential difference is B sub 1 minus 0 all over the resistance 1 ohm, or we can simply say that I1 is also equal to B sub 1. Okay, that is 1. Then now for current I, still the same, voltage over the resistance, the potential difference. So it says here that it is going to rise from B1 to B2. So it is more positively charged, no? The B1. So therefore B1 minus B sub 2 over 5. That's 1. Okay? So that is for current I. Substituting here on the equation, going back here, I sub 1 is B sub 1 plus the current I is B sub 1 over 5 minus B sub 2 over 5 must be equal to 5. Now rearranging the equations, this is 1 plus 1 over 5 is 6 over 5 of B sub 1 minus 1 over 5 of B sub 2 is equal to 5. So this will be our first equation. Now, so KCL at node B sub 2. So if we apply KCL again, current entering through a node must be equal to the current leaving. So current I is entering and both these two currents are leaving equals I sub 2 plus 4 amperes. So we will transpose I sub 2 is equal to I sub 2. Oh no, sorry. I minus I sub 2 is equal to 4. Now, substituting, since we already know the value of I, we need to determine the value of I sub 2. So, I sub 2 is definitely equal to the potential difference B2 minus 0 all over 2. Or simply, 1 half of B sub 2. So, substituting here, I is definitely equal to 1/5 of B sub 1 minus 1/5 of B sub 2. That is I minus current I2 is 1 half B sub 2 must be equal to 4. So, taking a look at this one, so this is definitely what? Negative. I think common denominator is 10. So, this is 2 plus 5. Or simply, negative 7 over 10. B sub 2 is equal to 4. And this is 1/5 of B sub 1. Okay? So, that is the two equations to be solved. No? Determining the values of B1 and B2, you may use what? You may use simultaneous linear equation, determinants, using matrix. No? So, since I think it is much better to use the simultaneous equation, elimination and substitution, no? So let us try to remove all the values of denominator in equation 1. So multiplying all the equations by 5 in equation 1, this will give us 6b1 minus b sub 2 is equal to 5 times 5 is 25. Okay, that is 1. And this one will multiply it by 10. So this will become 2v1 minus 7b2 is equal to 40. Now, taking a look at this one, this equation, 6b1 minus v2 is 25 and 2v1 minus 7b2 is 40. So, it is much better if you want to eliminate either or both. It's either you want to eliminate b sub 1 or eliminate b sub 2. So, for this case, I want to eliminate v sub 2. So, let's just say, color yellow, I multiply it by a negative 7 for it to become a positive 7. So, negative 7 times 6 is 42. Negative v sub 1 plus 7 v sub 2 is equal to 7 times 25. So, let me just grab my calculator here. 7 times 25 is negative 175. So, solving this will become 2 and negative 42. This will become negative 40. V sub 1, this is 0. Cancel out. Is equal to negative what? Let me just grab my calculator here. 40 minus 175 is minus 135. So, the value of our B sub 1 is definitely equal to divided by negative 40 is 27 over 8. 27 over 8 volts, or approximately or simply equal to 3.375 volts. That is one. Now, substituting the equation, either equation 1 or 2 or here. It's much better here. No? So, let us try to use the second equation, which is 2 times the B1 of 27 over 8 minus 7 b sub 2 is equal to 40. So negative 7 b sub 2 is definitely equal to 40 minus 2 times 27 over 8. Negative 7 v2 is equal to, let me just grab my calculator here. So 40 minus 2 times 27 over 8 is 133 over 4. That's positive, right? Yes, positive. So if it is positive, then divide both sides. So answer divided by negative 7. This will be negative 19 over 4. What happened to my drawing tablet? Okay. So b sub 2 is negative 19 over 4 volts, or simply negative 4.75 volts. Okay, so let me just grab the equation here, or the circuit here, and we can simply say that this is already 3.375 volts, 3.375 volts, and this is minus 4.75 volts. So we can determine the value of I is definitely 3.375 plus 4.75 all over 5. This will yield to 3.375 plus 4.75 divided by 5. This is 13 over 8, or 1.625 amperes. So 1.625 amperes. And presuming this to be I1, I1 should be equal to the voltage, which is 3.375 minus 0 over 1, or simply 3.375. And for us to check this, as you can see at node B1, if 5 ampere is entering through that node, that must be equal to the sum of I1 and I. Let us verify that. So 1.625 is equal, no, not equal, plus 3.375 must be equal to 5. So upon checking on the calculator, 3.375 plus 1.625, and definitely that is equal to 5 amperes. So this proves that 3.375 is a correct answer. How about the other one? Negative 4.75. We know that I is 3.375 amperes, and let us assume this to be going down. No, actually not, because we represent this as ground. So 0 and negative 4.75, and 0 is greater than negative 4.75. So therefore, it is positive to negative going up. So that would be 4.75. That would be our I2. I2 will be 4.75 divided by 2. And this will give you 4.75 divided by 2 is 19 over 8, or simply 2.375. 2.375 amperes. And I plus I2 should be equal to 4. Let us try. The value of our I is 1.625. 1.625 plus 2.375, and that is 4 amperes. Therefore, our node voltages is 3.375 and negative 4.75. These two answers are proven to be correct. Okay? So, whether you apply KVL in this part, they will come up with the same result. Any part of direction, as long as it is a closed loop system, or closed loop circuit rather. Okay? So that's it for today, and see you on my next video for another examples of William HAYT. Okay? So thank you very much.